My name is Amir Tamori. I was the purchasing rep, and I also assisted with CAD design on our beautiful 3D printer right here.
Hello, my name is Nicholas Nunez, and I was in charge of collecting and analyzing data collected during experimentation.
Hello, my name is Jose Zapata, and I was team lead on the project.
Hey, I'm Jamal Reed, and I focused on handling and analyzing the cured resin.
Hi, I'm Hunter Quibido, and I was the lead programmer on this project.
Hi, my name is Riley Donaldson, and I contributed to the design and build of our rotating bed assembly.
Hi, I'm Josiah Wig, and I assisted in the research, mainly focusing on the types of lenses to be used for the project.
I saw a similar device on a Tarkalian vessel. It was capable of replicating almost any inanimate object.
If we had one of these in engineering, we could make all the spare parts we need.
Our senior design objective was to create a new system to 3D print simple shapes using a new technique called volumetric printing. This way of printing forms a solid shape and eliminates completely the layer-by-layer techniques normal 3D printers use. Our goal was to be able to produce a cylinder, a cone, and a sphere to have a proof of concept to make sure our system could produce simple shapes. We limited the number of variables to have a greater consistency when printing parts. With limited time we were able to achieve our goals, but this is just a step towards enhancing our setup and refining it. A lot more needs to be done on the optical systems and resin, in which we as mechanical engineers do not have enough experience in those systems and did our best to research and develop a way to make it work.
Creating a working volumetric SLA 3D printer is a path towards developing one of the fastest and most accurate forms of 3D printing ever made. Typical uses include creating simple prototypes and medical tools, which can be done faster than other forms of 3D printing. But by volumetrically hardening the resin, we can actively develop frames for tools such as screwdriver shafts as they float in the resin.
Prior to the actual experimentation, the resin in the system must be set up and readied. The resin container, as well as all the magnifying glasses, must be wiped clean of any disturbances. The resin must be poured into the container, then magnetically stirred and heated for 5 minutes. The resin must be handled with care, with gloves being worn during use to prevent errors and to ensure safety. Polarized sunglasses must also be worn during the setup and experimentation for eye safety. System must be booted up with constant settings, which includes rotation speed and resin platform and projector height and distance, along with the desired projection being set up on standby, a red projection. Once settled, the resin must be then placed on its platform, ensuring that the container is completely centered with the projector and the lights must be turned off. Once everything is set up, testing is ready to occur.
The first step in the process is to begin rotating the resin through the system. To begin the printing process, switch the projection from the standby to a purple projection, which is the required wavelength for this project. This process will take approximately 2 minutes for the first print and approximately 1 minute for the following prints. To ensure quality of the print, the system and its immediate environment must not be disturbed, as well as the resin must not be used more than 4 times. The system must be monitored throughout the print in order to identify and stop the process once the print is complete in order to avoid errors. The print is complete when the complete object can be identified inside the resin before it begins to rise. Once completed, set the projection on to standby, cease the rotation of the resin, and carefully remove the resin container from its platform. With a pair of tweezers, slowly and carefully remove the print from the resin and clean the print with ethanol to remove excess resin. The print must be then post-processed under UV light for 2 minutes to harden, and this completes the print.
Our printer works by exploiting the kinetics of photosensitive resin. This resin is hardened by introducing a range of wavelengths of a certain frequency. Simply, colors projected onto the resin harden the resin at different rates, if at all. Therefore, in order to print some object, the corresponding silhouette needs to be projected onto the resin vat. Note that these projected images have what we call rotational symmetry. At least 2 of the 3 projections of the principal axis of the target object must have the same shape. Actuation of the resin takes place over the course of upwards of 2 minutes. Once cured, parts can be processed like other printers that use resin. Using a Raspberry Pi to control the entire machine, images are rendered on the Pi using an OpenGL framework, while all motors of the machine are controlled by the Pi using the I/O pins, all powered by Python.
So this has been a very difficult time for everybody, I would say, with COVID. So this is an interesting senior design project semester that we've had. Luckily, the internet we've had to use at our disposal, and with the emergence of Zoom and Teams from Microsoft, we have been able to collaborate without being in the same room with each other, but still being in the same kind of spirits. So we shared our CAD files that we created for SolidWorks so that we could print with 3D printers, which luckily 2 of our teammates do have 3D printers, FDM, but it's perfect for our applications which we could print some of our parts, including a lens, this projector mount, which went through a couple of different prototyping. A lot of different pieces on here are all 3D printed by us through CAD models designed by us. So I think that we can be pretty proud to display that as part of our progress. We took a lot of pictures of the specific prints that we did, which we will show in our presentation. Some parts obviously on this machine had to be bought, but that's okay. That's what budgeting is for. So as the purchasing rep for this group, I maintained our Excel sheets and made sure everything was up to code that we could send and get our parts ordered, which they did not take as long as we thought they would, but it was a good thing that a lot of planning goes into place, because when stuff is at a very distance, or we were remote working and with people that all has different time schedules, you got to make sure that everything is in order and in line and all written down on a sheet. I think one of the biggest issues that our team faced, as every other team faces, is no matter how hard you design, no matter how hard you plan, you never know what's going to work and what kind of tolerances are going to fit until you put it all together and you start putting the nuts and bolts together. So we did have some issues, at least with tolerances and stuff we thought were going to fit, and even ordering different parts, even stuff that's supposed to be a standard size was not a standard size, or was a little bit off. Even though we came through those kind of complications, we were still incredibly motivated to complete this project. I think all of us could say that this was a very interesting and attention-grabbing project that we decided to sign on to. So we were incredibly, no matter what obstacle, we try to overcome as much as possible. I mean, we'll maybe have some plans to show you the prototypes we had before, but I think our project has come a long way, and we've made a lot of different strides. And no matter how many different challenges our advisor has set for us, we have tried to ace them all with flying colors.
In creating the printer, many types of iterations and changes were made to satisfy the request of stakeholders. The team's stakeholder was continuously updated on the progress of the project and what was being worked on a weekly basis. It was through this open communication that the stakeholder was able to inform the team about the direction they want to go with the project. With this information, the team was able to implement any needed changes or upgrades that met the stakeholder's request. This method allowed the team to improve the overall design of the project through taking the stakeholder's design request and implementing it into the team's initial design, creating a more professional, effective, and accurate design for the printer. In terms of lessons for this project, prioritization is crucial when developing any complex system. This includes designating which features could be considered needs, wants, or other optimizations. Examining the importance of each design feature allowed our team to focus on the points that matter. A prioritization on early testing and simulation gave our team further insight on the basic operating principles of which our system was designed. Keeping a disciplined approach to developing any complex system in any industry will allow an engineering team to meet deadlines, meet or exceed expectations, and create an overall useful system.